4.3, number 116. Again, it's find critical values in domain of f. The function this time is sine squared. F of x equals sine squared x. All right, so what's the domain of that? Well, we know the domain of sine is all reals, so just squaring it should not change that whatsoever. So all reals, no concerns whatsoever. So if we find any critical values right now, they're certainly in the domain, because the domain includes all real numbers. All right, so we need to take the derivative and do two things with it. Set it equal to 0 and think about it as being undefined and see which x's make this true. So f prime of x is the power comes down, right? That's the outer function. The sine's the inner function. So using the chain rule, the 2 comes down, we get 2. Inner function stays the same. And then you differentiate the inner function and you get cos x, right? All right, so 2 sine cos should be our derivative. Now, where is this undefined? Nowhere, because sine x and cos x are both defined everywhere. Their domain is all reals, so when I take their product, it doesn't change at all, and multiplying by 2, of course, changes nothing about that domain. So therefore, there's no way that this derivative here could be undefined. So we're only concerned in this case, after a little bit of thinking about it, where this might be 0. All right, if 2 sine cos is going to be 0, we have two cases now because this is a product. Either sine is 0 or cosine is 0. After a little bit of thinking, a person should be able to come to what values make sine x 0 or cos x 0. And we're dealing with the full domain of all reals, so we have to give every single value here, and it'll be written as a small formula. Okay? For the sine function, we know the first time that sine is 0 is right at 0. Okay? So you have 0. And if you start going around the unit circle, you might say, in multiples of pi, right? You go halfway around. I'll draw a little picture. Here, right, we're starting out at 0. You start going around, right? Where is sine going to be 0 again? It's going to be 0 at pi, right? Pi. So pi. And now you go further. When's the next time it's 0? It's going to be 2 pi, right? So that's 0. It's also the 2 pi location. So 2 pi and so forth, right? It's going to be 3 pi and 4 pi. And if you went backwards, it'd be negative pi, negative 2 pi, and so forth. So you also have these, negative 2 pi, negative pi. So you got this going in both directions, right? So there's your set of values, right? I guess curly braces would be more appropriate. Curly braces. But we can write that as a formula, all right? We can just say all that is the same as saying 2k pi, and where k is an integer. This is the common way to write this solution. Okay? So 2k pi, any 2k pi, as long as k is an integer. When k is 0, we get 0. When k is 1, we get... I'm sorry, I wrote 2k pi. That's incorrect. Apologize. It's k pi, of course. Right. So when k is 0, you get 0. When k is 1, you get pi. When k is 2, you get 2 pi. When k is negative 1, you get negative pi, and so forth forever. Yeah, that was horrible. Shameful. All right. Over here, cos of x equaling 0 will be where? I'm drawing a small picture here very quickly. The first one is, of course, at pi on 2. Right? So you have pi on 2. Now you move up here. I got pi on 2. And you keep going around. The next time cos is 0 will be over here, right? At 3 pi on 2. And the next one will be over here at 5 pi on 2. There's 3 pi on 2. And so forth forever. Okay? And going backwards, right? If you've gone backwards, it'd be at negative pi on 2 is the same location as 3 pi on 2. So you'd have negative pi on 2 and negative 3 pi on 2 and so forth forever in that direction, right? So what's really going on here? Take some starting point. Pi on 2 is probably the most reasonable one. And you just add k pi, not 2k pi. Add k pi, and you will get all these other values, right? If k is 1, I'll get pi on 2 plus k pi, right, plus 1 pi is 3 pi on 2 if k is 2. Then I'll get pi on 2 plus 2 pi, which will be 5 pi on 2, and so forth, going backwards as well. So again, you have some sort of k value in here, which represents any integer, right? K is an integer. These little formulas for these solutions should be somewhat familiar from pre-calc. If not, I'm sorry that's the case. It will take some getting used to then if they don't seem recognizable. So x is that, or x is that. And so all of these values must be in the domain of the original function, because the original function's domain was all reals. So therefore we have our solutions here. X equals k pi, and x equals pi on 2 plus k pi. So now if we just think about this a little bit, is there a way to combine these two expressions into one expression? That would be nice. It's always nicer to have more concise expressions and solutions for problems. So the solutions over here were always along the x-axis. The solutions over here were always along the y-axis. Right? So it should be that if I start with 0, right, first solution for both of them together would be at pi on 2, right? So I would have pi on 2. The next solution would be here at pi, right? I guess with the first solution 0, but I was looking over here at the time. But anyway, so you have 0 for this one, you have pi on 2 for this one, then you have pi for this one, and you have 3 pi on 2 for this one. So another way to write this, right, going backwards would be the same thing, negative pi on 2, negative pi, and so forth. So there's our solution set, all written out in one statement, would be starting at 0 plus just pi on 2. Okay? So our total solution here as one statement would be just k, right, 0 plus k pi on 2, where k is an integer. Those are all the critical values, right? Our critical values for the original function f of x equals sine squared.